Okay. Good afternoon, everybody. So, Professor Armando already introduced me. I am a postdoc researcher here. Started working as a part of the group maybe like 2 months ago, around 2 months ago. And I specialize, as Armando said, I specialize in studying security of cryptographic protocols in quantum cryptography and also in classical cryptography. Except I am not a mathematician, I am a physicist. But but it's easy to confuse because my work is mostly oriented towards mathematics. Okay, so the story of this talk came when Professor Armando mentioned that the group here likes has been working on implementation of protocols in quantum cryptography, and but maybe they are not like don't have a lot of experience in the area of composable security. So maybe I can give like some sort of short talk to introduce to the general concepts and ideas behind the simulation security, and maybe you can use that to work and study your protocols better. So first, I wanted to motivate the idea of a specific framework for defining security in quantum cryptography, right? So from the most like fundamental level, or maybe from the most basic level, cryptographic protocols arise from informal descriptions of something that we want to do. For example, here I'm presenting you A wants to send a message to B without C knowing what the message is. Right? That's like the, let's say, normal words description of secure communication, right? Of a way of saying secure communication. I just want to send a message to another person and I don't want anyone else to know about it, right? But even though this is like from the point of view of our application is that, this is how I explained it, this is really not enough to formalize, mathematically speaking, how security should be defined. For example, here I propose like probable security generally requires quantifying its security features, right? So I want to say that C doesn't know anything about the message, but then how do we measure how much of the message C knows, right? So for that, maybe I can come up with some sort of quantity that measures it, but then I have many options. And which one is the one that is best? Which one should I choose for my specific application? There are more than one way of mathematically modeling protocols, modeling information, and also filling the details that are left from such informal descriptions. Like, let's say we want to start a protocol that does secure communication. And what happens if in the middle of the protocol we realize that something is wrong and we have to abort? So what is acceptable to happen when this fail case happens? For example, if the protocol aborts, is it acceptable for C to know the message? Like maybe, I realized it is wrong, but it's too late. C already knows the message. I know that C knows it, but it's too late. Maybe I don't want to let that happen ever, right? Maybe I want to say, no, C never gets to know the message, regardless of the protocol succeeds or not. Right? Or what is acceptable if, for example, later C finds out half of the message? So maybe there is a complex network of communication and it just happens that the information of the message gets transmitted between them, and at some point C gets to know some of the bits of the message, right? Maybe let's say half. So is acceptable that with those half, C can use the information that she got from maybe from the broadcast of the protocol plus this new information to get the other half? Like, is that acceptable or not? Right? So these are the kinds of questions that are not necessarily answered by the informal description, right? So we want to like approach security of a protocol as a measure of how well it does its job, right? So for that, I will propose you a classification. This is a classification that I just came up with it. It's not like a famous or like standard classification, but I thought it was useful to contrast different approaches to defining security. So first, I propose here the standalone security. So standalone security is what maybe naively we will want to do when you face this task, right? Okay, I have an informal definition of what my task should be. So maybe I will say, okay, so I want C to not know the message, right? So I will say that, the probability of C, of guessing the message is very small. Like, for example, I can come up with that kind of idea, right? And I can write a list of those properties and say, okay, the security will be given by this list of properties that I came up with, and they may imply certain things, but we like as I come up with them in a, let's say, naive way, they don't necessarily immediately imply everything that I will want to imply. So one of the examples that I'm putting here is like maybe guessing probability. I want guessing probability to be low, whatever. I want mutual information. I can talk about entropy. The entropy of the message is high, is low, etc. So one step further, I present you the indistinguishability-based security. So we define this type of security in this approach is defined as a list of indistinguishability relations between the variables of the protocol and the respective ideal outcomes. So what I mean is, for example, like, I want that the protocol, like at the end of the protocol will have some outputs, right? And I want that the joint distribution of those outputs has certain shape, ideal shape. And then I will say, I want my distribution, the real distribution of my protocol outputs to be indistinguishable from this ideal distribution that is what I will want. Right? So this is, this is a particular example of the approach above, the standalone security, except is restricted to certain type of statements. Then we got simulation-based security. So in simulation-based security, the security is given as a list of, I have put here in parentheses, implied indistinguishability relations, between the executions of the protocol and its respective ideal functionality. So instead of me talking about certain distribution of the value of the certain random variables to be indistinguishable from another ideal distribution, now I'm talking an execution of a protocol to be indistinguishable from another type of execution that I call in here the ideal functionality execution. So this is a little bit stronger, depending on the situation. It can be very much stronger or can be no stronger at all, because it actually contains all the information on the protocol is being manipulated, right? If there are messages going back and forth, inputs, outputs, everything that is being like communicated in the protocol will appear in the execution of the protocol. And if we want two executions to be indistinguishable, it means that everything has to look exactly the same. So this is the strongest version of these three tiers that I'm putting here. And to illustrate a little bit better the differences between these three things, I'll propose you an example, right? So let's talk about key distribution. So key distribution will be the main example, but because it's basic, it's something that we all are familiar with, and it's I found that it's a very like nicely behaved task to explain this kind of things, right? So we start with the informal definition of what I want. So Alice wants to share a random n-bit key K with Bob without Eve knowing what the key is. So, okay, so I will put this in the form of a diagram. I have Alice here, right? Sorry for my art. I have Alice here, Bob here, and Eve is here. So this line here means that no one gets, like neither Alice or Bob get any input. There is some sort of communication going on in these lines, right? So Alice gets certain information, Bob gets certain information, and Eve gets certain other information. And as a result, Alice is able to output the value Ka, Bob is able to output the value Kb, and Eve is able to output this, I'm calling a value Z. So in this diagram, what type of statements will I want to say, okay, whenever this holds means that my key distribution protocol is secure. So let's start with the first approach. So the standalone security. So I will just say a bunch of, it seems a bit that I'm trivializing the issue, but I'm going to say three things that may have been, and the reason I'm putting that, I am presenting them as I am, is because in each of these cases, it may have been in some other way, but I chose this way. So let's see the first one. So I demand that Ka is equal to Kb, except with negligible probability in it. So this property I'm calling the property of that the key is shared, right? So we want both parties to have the same key, right? That's important, right? So I'm demanding that to happen except with negligible probability. So I am allowing that maybe it doesn't happen, but the key aspect that I am adding here is that if it doesn't happen, I can make it very quickly happen to an arbitrary degree. That's the reason. That's what negligible probability here is, right? Everybody here, I'm assuming that everybody here knows what a negligible function is. So if any of you have any questions during in any moment, I'm very happy answer them. So then the second condition I am putting, right? The distribution of Ka in uppercase and in the random variable Ka is uniform in the set of the n bit strings. So this is the property I'm calling that the key is random. Right? So now I am not allowing this Ka to be close to uniform. I'm saying it's uniform, right? Which is a choice that I made, right? And it is somewhat arbitrary because in principle, I am kind of like just choosing things that sound good to me, right? And then the third one is the accessible information that I am writing here. And I am writing this last one already like looking forward to a protocol that can be potentially be quantum, right? So what if the information that Eve gets in this part, in this diagram, she's outputting here some value Z, but the information she's getting from this arrow may be in the form of a quantum system, which is the case in quantum key distribution, right? So let's allow that to happen. No? So I will define the security as the third property. The accessible information, which is this quantity that here, is negligible in N. So the accessible information is not a quantity that appears too often, right, in information theory. So let's define what is it, right? So accessible information between a classical, accessible information is defined over classical quantum states. So a state that is, for example, that you have a joint state between the systems Ka and E, and accessible information is defined over the classical system A and the quantum state, classical, non-classical system, classical state A and quantum state E. So it is the maximum mutual information that you can have over all possible measurements that you can make on the system E that as an outcome of the measurement, you obtain the random variable Z. So from all the possible ways you can measure, Eve can measure the side information that she obtained from the protocol, she will choose the one that gets her the best mutual information with the key, and she will do that, right? And she will quantify how much information she got. So this is the best she can do. Do you guys agree that this is the best Eve can do? Does anybody see any problem with this quantity, with the third point here? You choose the best measurement and the measurement that gives you the most correlation. And I'm saying that the one that is the best, it's still negligible. That gives you negligible information. Should be strong enough, no? And of course, I chose this because I have here not counter example, but just the particularity of the accessible information. Right? So there is a property of quantum systems that it's less used nowadays, and maybe the term itself start getting confused with other works. But there's a property that's called the locking information of the locking of information in quantum systems, right? And what I'm describing here is an example of this event, phenomenon. So consider the following quantum state that you have here. So I am proposing here in the equation number 2, I'm proposing a state that is tripartite, right? And it's classical in X and Y, and it's quantum in E, right? So the state that I'm proposing here, as you see, is a mixture, right? That is uniform in the values of X and the values of Y. Values of X are only 0 or 1, and the values of Y are treats, right? So we can have a value 1, 2, or 3, and you have an M tuple of those. So Y will have, for example, if M is equal to 3, Y could have a value of 1, 1, 2, for example, right? 3 numbers from 1 to 3. And then you have some state of some system that is arbitrary. You don't say anything about what is happening here, but this is the condition, this is the state of E condition of the value XY here. So this is this is the state that could be shared. This is a state that, in principle, could be obtained in a protocol that has a diagram of this. So, and now I'm saying, imagine if the condition states that I have put here are of this form, right? Are this exactly this, right? So, it can be shown that if I select row XYE to be this specific state, then I can compute the accessible information, and I will obtain that this quantity is bounded by 2/3 to the M halves, which is a negligible function in M. which case M is here the size of this tuple, right? However, if you notice, right, this, sorry, I have not explained what it is. These are the tensor products of M Pauli operators. So for example, this value sigma y will be something like if, let's say M is equal to 2, right? And y is equal to 1, 2, right? So this will be sigma 1 tensor sigma 2. And sigma 1 will be the X Pauli operator, sigma 2 will be the Y Pauli operator, and sigma 3 will be the Z Pauli operator. So the state that we have here is always some eigenstates of elements of this tensor product of Pauli operators. Right? Now, if I fix the value of y here, it just so happens that the state with x equal to 0 is orthogonal to the state with x equal to 1 when y is fixed. Right? So this is easy to see. I mean, in many ways, I don't know if you will be interested in knowing why, but this is easy to compute, right? You can compute that, for example, the trace distance between the state with x equals 0 here and x equals 1 here is 1, right? And what does this mean? Well, this is here. Like for fixed values of y, the states rho 0 y e and rho 1 I y e are orthogonal. So what does that mean for security or anything? Right? So this means that if, for example, I were to consider this value xy as a key, right? I will absorb these two things and will make it, okay, this is Ka, right? So what this is saying is that if an adversary will get to know the y part of the key, right? Then with that information, Eve can perform a specific measurement that will give her the last bit of the key. You see? So having all but one bit of the key allows you to get the last bit, which is, maybe you can think, well, it's not that bad, right? But it's something that it's not necessarily desirable, and it's something that was not necessarily obvious from the definitions that I put of what security means. And the reason this wasn't obvious from when I first stated the security is because this happens in the specific context of Eve getting information later before doing the measurement, right? So when we define here the accessible information, this is maximizing over the messages, but these messages are not informed by part of the value of K. But it's possible that in the context of a network of a lot of computers sending information, eventually, not even by accident, but as part of a very complex communication network, Eve, what here is considered Eve as an adversary, may get information later about that key. And considering that particular case in which she gets everything but one bit and can use that bit to get the other is just an example of, it showcases our inability to consider every possible context, every possible context at the moment of defining security. And that's the issue that we want to address with composable security. We want a security framework where every context is already considered without us having to think about one by one, how will we deal with that? Do you understand? So moving forward a little bit, we have the second approach, which is the indistinguishability base, right? So here I am saying, okay, let's define the security of key distribution through indistinguishability statement. So here equation 4 is that. So equation 4, if you see, it's only one statement instead of being 3. But that statement contains everything, right? So by me having a uniform mixture, like having this 1 or 2 to the n, I impose the randomness, right? By these two values being the same in this mixture, I impose that the key is shared, right? And by this being a tensor product of something that does not depend on K here, right? I impose that Eve doesn't have information about it. So all three things are all stated in a single beautiful statement. It just happens that this statement is strong enough to imply universal composability of quantum key distribution, which is, when we understand what universal composability is, I have the example, this is the reason I was preparing the tablet. I will show you how this equation here implies composability later in the talk. And finally, for defining in a simulation-based framework security, what we have to do is the first step is to define what key distribution means in the context of a single service that does the job for you in a trusted way. So imagine if I have a machine, a third-party machine, that I can just use it and it will do key distribution for me. And I can trust that it works, right? So what will that machine do? And by defining what that machine does, I am tacitly, or maybe, defining all aspects of it, including the security state. So first I'm just saying, okay, this is just a small exercise, and all the examples that I'm showing here are very simplified in the terms of notation, in the terms of like, for example, I will not be considering session IDs and a lot of other things that usually are considered during the statement of this. I just want this to be as high level as possible, so it's very understandable, right? So this functionality is a program, right? It's a program that is parameterized by a set of parties, Alice, Bob, and the eavesdropper Eve, and it will generate keys of size n, right? So it's parameterized by that n value too. And what it does is that upon receiving the message from Alice, hey, can you send keys? Then the functionality will sample a value, k, of n bits randomly, and output it to Alice and Bob. And then I will tell to Eve that a key was shared, and then it will stop. So this is a single-use key distribution machine. So that sounds like this is what we wanted to do, right? It sounds like if I will want to do key distribution with someone, and I will want a third party to do that, that's what I will do. Just please, can you produce a bit string of n bits and send that to us, but not to the other person. Right? Now, I am allowing the machine to communicate to the adversary here that the key was shared, which is key, right? It is key because in an actual protocol, I understand that maybe I will have some limitations. Maybe I will not be able to do it without everybody else noticing that I did it, right? So I introduced that by the functionality, letting the adversary know that the key was shared. So this is also an example of how I implement my potential limitations inside of the functionality in order to have something that is realizable, maybe. And in the emulation or in distinguishability statement is done over networks. So what I'm saying is that if PA here is the program that Alice runs in a protocol, and PB is the program, Pi B is the program that Bob runs in the protocol, then I will want that the left side, which is with denotes the programs running with the communication channels, right? It's indistinguishable from the right side, right? Which is just the machine. Depending on the specific framework, this diagram might not be applicable. Right? So there are frameworks in which this diagram is okay. Some other frameworks need you to add some other things to the diagram. But I'm just showing you this to say that, well, this is what we attempt to do. We want to show that certain programs are equal to certain other programs in the context of a network. Okay, so there are many ways of doing this, right? That's just like as an example, like notable examples, I will note the Universal Composability Framework, which is not the first attempt at this, but maybe the one that stuck the most, and the one that maybe is the main reference for composability, right? Then, because this is a quantum group, I will want also to talk a little bit about the Quantum Universal Composability Framework, which is a generalization of the above. And then I mentioned the next two because they show a little bit of two directions that we can take from there, right? So there is the abstract cryptography framework, which what it does is that it generalizes universal composability to the point on make it applicable to any type of machine that I can think, right? So if you want relativistic cryptography, if you want well, types of machines that are not quantum computers, but maybe some other bundle of computation or implementation of computation that it's like exotic, that it's just not equivalent to what we use, you can use the abstract cryptography framework to immediately apply, create definitions and protocols in that model of computation. So it is more general than even the quantum version. And then you have the simplified UC framework. I'm missing an E here, the simplified UC framework, which is a framework that is a little bit more limited. It's not universal composability, but it gives you certain composability properties that are enough for you to implement secure multiparty computation. So it's basically one that you can use for oblivious transfer, right? When you want to prove that your oblivious transfer is secure, for the purposes of using it for secure multiparty computation, you can use the simplified UC framework. Some things are possible in the simplified UC framework, which are not possible in the universal. Okay, so we can go now to the universal composability framework. So this is what we are going to talk about the most. And this framework, even though I just told you that there are several frameworks that can be used and we can choose, all of them will follow the same principles of this. So understanding this framework, it is like basically allows us to understand the other ones too. So in the universal composability framework, the main object of analysis are protocols. And protocols are understood as a set of algorithms, or most better said, a big algorithm that is designed to run in a distributed system. Like, so you have different systems, like maybe you can call it devices, machines, can even be several parts of the same machine, right? Of the same computer, depending on how do you separate them. And they are running a protocol that involves communicating among each other and sending and using the messages that they communicated to do computation and send other messages. And these individual parts are called machines, right? These individual elements of the protocol are called machines. So each program runs independently in the sense that this machine is going to run, the program is designed to run independently of what this machine is doing, or maybe this machine exploded, but this will still run. No? But they will be able to send and receive messages from each other. So they run independently, but their outcomes will depend on the communication that happens between them. And each program has its own individual inputs and outputs. So each machine can be understood as its own little thing, and the protocol can be understood as the aggregation of all these little things. Right? So formally, a machine is a triplet. It's a triplet that has three. It has the first component of the triplet is the ID. So each machine will have some sort of identifier to make it unique, right? Then you have the communication set, which is a set of communication channels that connect this machine to some other machines. So in principle, not all machines inside of the network will connect to everybody else. So they may be connected only to one, to maybe to all of them, maybe to some subset of them. And depending also on the framework, these communication channels might be classified as, for example, input, output. Maybe some of them are called backdoor information, etc. But for the moment, we will just say that they are communication channels and we can use them for arbitrary communication. And finally, the actual program of the machine. So these three things define the machine, and a protocol is a set of machines that satisfy some set of compatibility requirements. And so not every set of machines can be a protocol, but sets that make sense. Right? So we'll not delve on what does that mean to make sense, but set of machines that are connected in a way that is sound, those conform a protocol. One of the important aspects that I'm putting here is that a machine can have communication channels that go out of the protocol. So they communicate to the outside, let's call it, right? And these are the ones used to get the external inputs and give the external outputs of the protocol. And finally, protocols may be parameterized by a security parameter K. So we can call a protocol, like for example, this thing here, right? And it will do certain thing whenever K is equal to 1. It will do some other thing when K is equal to 2. It will do some other thing when K equal to 3. But this parameter, this security parameter applies to the protocol completely. So depending on the value of K, maybe all of the machines do something different, but they are all agreed that this is the protocol we are running with this security parameter. So you could say that a protocol can also be understood as a sequence of individual single non-parameterized protocols. Yeah. Okay, so to study the protocols in the context of composable security, we will need to define what does it mean to execute the protocol. Now, executing the protocol from the in the normal point of at first glance, what it means is just run it, right? You just put the inputs, let it run, it gives you output, and that's executing a protocol, executing the. But in this context, it's something different, and this is something different because these executions is what we will be using to define to define indistinguishability between two networks. So first, when we execute a protocol in this context, the first thing we will do is we will grab our protocol and we will create a new protocol, like temporary protocol, let's call it. Like maybe let's call it, what's the word? Like virtual protocols, if you will. This protocol contains two extra machines. One machine is called the adversary, and the other machine is called the environment. They have specific properties. So the environment is a machine that has a communication set that is connected to every communication channel that goes out of the protocol. So if you have originally, for example, had two machines, these two machines, they receive inputs from the outside, from the users. Like they give, this is what I want to do, then they do the protocol, and then they output to the users. Right? So these lines to the user, they will connect to the environment. Right? And they are connected also with the adversary. And it has one single communication channel that goes out, which is used to get inputs and outputs. So in short, the environment has one line, one communication channel for inputs and outputs, and a lot of communication channels that connect to every loose communication channel in the protocol itself and with the adversary. Then you have the adversary. The adversary has a set of communication set that allows it to receive information from every machine in the network. So all of the machines, regardless of who are they connected, will be augmented with an extra communication channel that goes to the adversary. And that is used to model how when you run a protocol, for example, if you broadcast some information, this information is also learned by the adversary, like people who are listening, right? So these extra communication channels, what they do is basically used to model that. So this resulting set of machines, our original protocol, with the adversary, with the environment, is a new, let's call it virtual protocol, that is the one that we are going to execute. So this is a diagram of what I just said. So imagine that our original protocol, right, is this thing that is here denoted by pi. And then we have these boxes here, which are the machines that conform the protocols. And as you see, these lines here will represent the communication channels. Right? So you see U1 might be connected to some machine here, to some other machine here. UN will be connected to some machines here. And all of them are connected to the what we call the adversary. Then these lines that go here, if you understand the protocol as this box here, right? There are some lines that if we remove the environment, they go out. So these are the inputs and outputs of the protocol. The environment is connected to those, right? Sorry, and it has an extra wire for inputs and outputs for itself. So this bigger protocol, this virtual protocol, has only one input and one output. With I think I forgot to say it, but the output of the environment is always forced to be either 0 or 1. It's a binary output. Is this more or less clear what I'm talking about? There are no variables in the picture. They're just the communication channels. So this thing will hold the output of the environment, and this is the only output that there is because every other output got connected to the environment, right? This was an output before of the protocol, but now it goes to the environment. And the output of this new compound protocol is just this one here. So this is input output. Okay, so is everything more or less clear? More or less, okay. I take that. Now, what is an execution of the protocol? So we will denote by execution of the protocol pi with an adversary A and an environment K, right? As a function of the security parameter, E, as a function of the security parameter K and this Z, which is the input of the environment. So this is the input that comes here. Right? So when you execute a protocol, you get an input and this Z represents that input. Right? So when we talk about this, we're saying we all agree that we're going to run our program associated with security parameter K. I'm going to put an input of Z here, and I'm going to let everything run. Everything will do its thing until everything halts. And after that, everything has halted, this will output something here. And what it will output, it depends on the program that the environment runs, which can be any program. The only condition is that it outputs 0 or 1. That's the only condition. Also, there are no conditions on what the adversary runs. So these two are basically, I'm putting in them there, but I'm not saying what are they doing. They can do whatever they want. different environments will result in different execution, the same thing with the adversaries. So we denote by this exec that we have here, depending on K and Z, the random variable that is associated with the output of the execution of the joint programs, as I just explained, on input Z and security parameter K. Now, we denote by exec the same thing, but without the Z, just the K, right? The ensemble of all the execs over all possible Zs. So we'll create this big random variable that contains all possible outcomes of all possible inputs of the environment, right? And that's exec without the Z, it's just the K. Now, we say that a protocol pi UC emulate, in this case is UC from universally composable, emulates a protocol phi if for any adversary, and this is kind of like, this is like maybe something that you can repeat like 20 times every day in the morning, so it will like burn into your brain and then you will never have to like read the definition again, because it's a little bit like, can feel a little bit convoluted at the first time. Like if for any adversary A, there exists another adversary S, which we call S because typically it's called the simulator, right? Such that for any environment, big E, the ensembles of the exec this, which is are these guys here, right? And the exec of this, which is the same but with the protocol phi, are indistinguishable in K. So you say the two ensembles are indistinguishable because there exists a statistical distance that you can use to compute what is the difference between the two. And if that difference is negligible in the security parameter, we'll say that these two random variables are indistinguishable, and hence P UC emulates the protocol phi. So again, for every adversary, for any adversary, there exists a simulator such that for any environment, the executions of P and phi are indistinguishable. So that's what it means. And this definition of emulation is at the heart of composable security. So you have to learn how to show that this is, but like proving security in composable security basically means proving that this happens, right? Now it feels a little bit overwhelming. Like, how can I prove that for every adversary there exists a simulator such that for any? It looks like there's a lot of adversary, there's a lot of environments, right? And these objects here, these are ensembles of infinite dimension. Like, it looks like I have to do a lot. We'll see in the example that this big thing can be compacted into a more digestible task for a person trying to probe security. And now I just want to make a point here that I never said that the adversary or the simulator or the environment are polynomial time. In the original Canetti paper, they are polynomial time. And if you don't consider polynomial time, this is statistical UC emulates. If you consider them polynomial time, they will be computational UC emulates. Okay, so then just like a little bit like a graphical way of showing what I just said, right? So you have protocol P and protocol phi, right? And the protocol phi has the adversary here, right? And then you have the environment, and the environment receives an input Z and will output the exec, the Z, right? So let's fix the K. Right? And then the same thing here, except here I will, instead of putting A, because this protocol is in principle different than this, right? I will put a simulator, an S, that depends on A. So it should be something that is constructive from what A does. And it will kind of like cheat, like, let's say like cheat the environment into thinking that this, into like, not necessarily thinking that, but into not being able to tell if the environment is all of these wires are connected with this pair or with this pair. That's the idea of the simulator. Right? And what you want to show is that for all the Z's, right, these random variables here associated are negligible in the security panel. Is that maybe a little bit more clear if you say it like that? Okay, now we return to the topic of ideal functionalities. So ideal functionalities are understood as trusted machines that perform the desired task, right? This is exactly as I just explained you at the beginning. Right? So the formalization of a cryptographic task then is going to be done by defining the respective ideal functionality, because you see the security is already defined here. You know what security means. It means that your protocol emulates the functionality, right? So you don't need to define security anymore. The only thing you have to do is define the functionality. That's your task as a person trying to model the task. Right? You just define the machine, define the algorithm that the functionality is supposed to be doing, and everything else is already done. You don't have to come up with, maybe the mutual information it's negligible or something. You don't have to do anything like that. You just have to define the functionality, and everything else falls by the framework, which is the great advantage of using these things. And so we have here, right, this diagram that I'm putting is the network that is associated with the IDLF, which means the ideal functionality network, which is the functionality, but the functionality I'm going to augment with these boxes that are called the dummy party variables. So these are meant to be the machines in the network. But now, because the functionality is doing what the machines in the network will be doing, they are not needed. So we put it here just by technicality, because we need the environment to think that the environment is talking with the machines. So we have these dummy things that all they do is to forward the information from the functionality, but they do it with the ID of their machines. So when the environment talks with them, they're talking with the correct machine. But they don't do anything. Everything is done here by the functionality. So what we have to show that something is secure is to show that the execution of, as I showed you, of the protocol is indistinguishable from the execution of this thing, that I'm showing you here, like with the adversary and with the respective dummy parties. So I just dedicated one slide to say that. Right? So what does it mean a protocol to be secure? A protocol P UC securely realizes an ideal functionality F if P UC emulates the ideal F, which is exactly this protocol that I'm showing you here. So that's what security means. Right? So compared to the first approach, even the second approach, it feels like there's a lot to it, right? It feels like, oh my God, I have to think about the adversaries, I have to think about the environments and which environments are better than others. Where do I look? How do I even do anything with this, right? Yeah, so we'll talk a little bit more about that. But the important thing is to understand that security comes from the definition of emulation, right? Now, wait, why? This is all fine. This is all perfect, right? But why does it call universal composability to begin with? Right? It is called like that because there exists this theorem. It's called the universal composition theorem, which tells us that if you have like I will not want to write the statement because the statement is a little bit complicated. It has to give the deal with details of compatibility of subroutines, right? But I can give you like this diagram. Right? So imagine that you have this protocol, right? And this protocol here, the machines row 1 and row 2 are calling the functionality, right? So this is the ideal functionality, the DLF, right? And now what I will do is I'm going to replace this box here with some protocol pi. And I'm going to call this new protocol row of the functionality replaced by the protocol pi. So this is a protocol inside another protocol, right? So if this protocol pi UC composable, UC securely realizes the ideal functionality, then row where the functionality is replaced by pi, UC securely realizes row. So this is the universal composition theorem. If the subroutines are all the subroutines here emulate the subroutines here, then the big program here emulates the big program here. So that's the idea of composing. That's the idea of you replacing a single thing with two things, or replacing two things with a single thing. Right? You're like building Legos, let's say, but with protocols and machines. And the universal composition theorem tells us that if I'm able to prove something, let's say, simpler, the more complicated version of it just falls because of the universal composition. And that's also the second big use of the framework. Right? Not only it allows us to define security easily, but also it allows us to use previous results to immediately obtain new results, like basically by playing Legos, as I'm saying, right? It just automatically follows. Okay, so there are some additional features that I am not going to discuss, but I'm going to mention that they exist, right? First is party corruption. So far, we just dealt with an adversary that can get maybe some sort of backdoor information from the parties, but the parties themselves, they all behave honestly. But it can be that parties themselves behave dishonestly. Like that's the case, for example, in protocols like oblivious transfer or any arbitrary multi-party computation, in which maybe our adversaries are not really external, but are internal to the set of parties performing the protocol. Right? So in those cases, that is introduced by you. When you define the protocol, you have to add an extra clause saying, okay, if the adversary, like, because you have to always have an adversary, if the adversary wants, let's say, like, if the adversary requests, then the adversary can control the party up to certain amount of degree that we can choose. So we can say, okay, if the adversary decides to corrupt the party, then now this party is going to behave either a bit differently or arbitrarily as dishonestly as you define it in your own, when you define the protocol. And the hybrid models, which are type of models in which you can assume the access to certain functionalities, right? Ideal functionalities. And these are mostly used for reductions. For example, if I work in the random oracle model, I can do protocols that have random oracles inside for free. I just put them there. Right? You can call the random oracle. Right? Or if I have a public infrastructure model, which is the practical version, the more practical version of it, right? Which is this trusted entity that holds public keys, and you can ask, what's the public key of IBM, and then they will give you, and then you trust that this is a correct public key, right? So this is a functionality. In this framework, it's an ideal functionality, right? So we can say, okay, in the public key infrastructure, certain protocol of public key protocols are universally composable security. Now, what happens when we go to quantum? So there is UNRWA's quantum UC security framework that it's a direct, like it is based on Kinetis, the one that you just saw, and it's a direct generalization of it. The only difference is that it, instead of using Kinetis, properly uses what we call interactive Turing machines. And UNRWA's uses quantum computers, it's essentially, right? So it defines quantum computation as a set of superoperators, blah, 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 but in the end, it's trying to abstract the idea of the computers now. They can run quantum programs and they can communicate through quantum information. They can send them entangled states, blah, blah. And there are two interesting results that I just want to show you here that exist in that framework. One is the quantum lifting theorem, which is that if you have two classical protocols, and you can show that those protocols are statistically secure in Kinetis framework, the one that I just showed you, right? Not statistically secure, what I mean is that one statistically secure emulates the other, then these same protocols will emulate each other also in the quantum using framework. So this means that quantum classical security, statistical classical security lifts in the quantum universe composability. And then you have maybe the most famous result of this framework, which is that there is the reduction from multi-party computation to bit commitment, right? It has been proven that oblivious transfer, and by that, secure multi-party computation can be quantum UC securely realized through a protocol in the bit commitment hybrid model, right? So you assume that you have access for free to bit commitments, and you use those bit commitments as a ideal functionality to realize oblivious transfer. No? And you can do that in a UC securely way, in a quantum UC securely way. There is no way of doing that. Well, it's believed there is no way of doing that in the classical sense. So if you have access to free bit commitments in the classical sense with classical protocols, I still cannot UC securely realize the oblivious transfer. Okay. All right. So this is the example that I wanted to show you. So I'm guessing we can see the, wow. It's a little bit delayed, but okay. Maybe is there a way of making it bigger here on the screen? I think it's better. Okay. So okay, let me return to this. Just a second, and then I will come back. So the example that I'm proposing here is to try to prove that the quantum key distribution is universally composable. And how are we attempting to do this? We're going to use the result that we already showed for the second, remember, this indistinguishability relationship, to show that the quantum key distribution protocol UC securely emulates this functionality that we see here. Now, if you see, I put a prime in there is some feedback. I put a prime here in the definition of the F because it's not quite the same key distribution functionality that we showed at the beginning. This has an extra, let's call it feature, like as the software companies like to call it. It's a feature, it's not a bug. It's not something bad, it's a feature. And we are allowing Eve to deny the service because we cannot prevent that from happening in actual quantum key distribution. So we allow Eve to capture information. Maybe she wants to measure it, maybe she wants to keep it. And then what's going to happen is that then when they do, is everybody here familiar with quantum key distribution? So what's going to happen is they're going to be done some test of correlations. The test is not going to be passed, and the protocol will abort. Right? So Eve can always say, okay, you guys, you will not get a key because I decided to steal all your quantum information. And this has to be accounted for in the functionality because if not, we cannot implement it. Right? So the new functionality is the following. Right? We have three parties, Alice, Bob, and the adversary. In this case, we call it eavesdropper Eve. And the size of the output key. And what it will do is that Alice will request keys from the functionality. Right? From receiving the message, send keys from Alice. Instead of generating the key and send it immediately, which is what it did in the other version, it will instead send a notification to Eve that the keys were requested. And now Eve can respond to the functionality in two ways. Either first send the message, say, okay, allow it, in which case it will do the normal thing. It will sample the key and then will output to Alice and Bob and it will let Eve know that the key was shared. Note that Eve doesn't get the key anyway. It just chooses if it wants to let it happen or not. Or if Eve doesn't allow, what's going to happen is that it's going to communicate to Alice that, sorry, no keys could be shared. Maybe here, Alice and Bob, right? And also to Eve, just to confirm that everything went as planned, and then halt. So everything, is it clear, this functionality? All right, so now I'm going to, so let us write, so this will be a not proper proof, it's just gonna be a sketch. And the idea is for you to showcase you, because I just show you the definition. And the definition, I understand, it does feel very overwhelming. So there is some feedback, sorry. So I want to show you that in practice, you can actually, like, it's doable, right? This is what I wanted to say, right? So we start with the following. Like, so let's call the protocol of quantum key distribution. We all know what it does. I'm not going to get into details what it does. I'm just gonna use Renner's result and the generalities of what happens during the protocol. So we have the protocol that Alice runs. So this is Alice's program. We have Bob's program, and we're going to model the communication between Alice and Bob as first sending the information to Eve. Note that Eve is the adversary. I could put an A here. Maybe I should. I will. Just to be on the same notation as the thing that I was explaining before. And it will communicate here. So you have these boxes, right? So you have Alice's program, Bob's program, and the adversary program. Right? And there is some communication also between them. So this is what we have here. So this is the protocol. And when we want to compare executions, what did we have to add? Well, first we add the adversary, which is already added. And now we will have to add the environment. So let's put the environment here. And this is how we are modeling in the sense that, because how we will do it is that when Alice, for example, there's a prepare and measure type of quantum key distribution, Alice will send, let's say, the photons to Bob. So what we will model is that Alice sends the photon to Eve, Eve does whatever she wants, and then sends it to Bob, forwards it to Bob. Alice communicates with Bob. This wire of Alice communicating with Bob represents, for example, all the other parts of classical communication, like the error correction, all the things, but particularly the quantum part, this is what I am putting this wire. I am not being completely like formal with these things. I just want to explain you the big aspects, right? So Alice and Bob, they communicate with each other, they communicate with it, but they also communicate with the people running the thing, because this, we call this Alice, but in reality, this is a computer, right? And the computer will output a key, right? And will output to this wire. And then Bob will output also a key, right? So now, these keys have to, these wires have to connect to the environment. This is what we said that the property of the environment, and this thing also has some output, right, which will also connect to the environment. So this is the protocol execution scheme that we want. So now what will be the ideal execution, right? So the ideal execution will be, we have here the functionality of key distribution, which is connected by technicality again, right? This is not like some frameworks don't even need this, right? With the dummy variable, dummy machine that represents Bob, dummy machine that represents Alice, that only forwards the information, right? Right, and it's connected here with what I will call the simulator, which is the respective, the associated adversary in this context, right? So now this comes here, and then we have the environment. So the environment here. And we will do the same thing. Like this connects here, and this connects here. So, well, there is also the wire to the external, and this is the real world protocol, and this is the ideal world functionality. Are we clear towards what I explained? This is all right. So now, what is it that we want to do? So think about it. Let's repeat again, right? For every adversary, there exists a simulator such that for every environment, these two things are indistinguishable. Now, the output of Bob. So typically, we set the output of the environment to be 0 or 1 because this is basically a guess. This is basically, you can interpret it, it's just a point of interpretation, right? If it's 0, you are saying, I think I'm interacting with these people. If it's 1, you say, I think I'm interacting with these people. If the two things are indistinguishable, it means that it cannot even tell, right? It just says something and it may guess or not. So, like in the sense of like the outcome of this is independent of with who you are interacting. Right? Exactly. So the idea of this is the following, right? So think about it, right? I am saying for every adversary there exists a simulation for every environment, but what I really mean, but that's not what I really mean, but what I also mean is that imagine this environment getting some output that will resolve. First, imagine the environment running some program, whatever program. And then over that program that's running, it gets some input, right? And then that input will trigger it doing something, right? Which is some program too, right? In the end, it's just running a program, right? And now imagine the adversary, which is running whatever program, and the environment can feed into the adversary to control it in such a way, but at the end of the day, the combined action of these two guys is just a program. It's just some program. And what we want is basically that this program that is here, right, is receiving certain inputs here, right? Is receiving certain inputs from this wire, from this wire, from this wire. We can show, right, that that the inputs that the environment receives here are the same. We can guarantee that, then we achieve what we want. In the sense that the relationship between the numbers here and their probabilities, there's this joint distribution of everything that is coming in here, is indistinguishable with whatever is coming in here. If I cannot manage that to happen, I'm done. So for that, I'm going to do the following. This is the standard way in which this is done, right? So I'm going to define the simulator is going to be consistent in two parts. It's going to consist in a program that runs the same, a box, let's say a machine, that runs the same program as the adversary. So this is basically a copy of the adversary, right? And then something here, right? And this here, for example, in the abstract cryptography framework, and I like it that much, I like it a lot, they call it a converter. A converter is a machine that transforms what the functionality gives into something that looks like what the protocol gives. This is the idea. Right? So in our case, right, what will be the converter? So what I propose to you today, right, is that the converter is a program that runs a fake version of quantum key distribution. So the converter has here a fake Alice machine and a fake Bob machine, right? And the whole inside of the simulator looks very much like this. Now, this obviously has a connection here with the functionality, right? And this thing here has a this wire here, right? Gets out, sorry, which will be what is connected with this thing, which ideally, right, should be what is connected with this thing. So what we want is that the joint distribution of the traffic in the blue wires is the same. Right? So the ongoing distribution depends only on the environment. So this will be the same because the environments are the same. We just have to make sure that the upcoming distribution is the same too. So what the simulator can do, and this is like, let's say, the solution is always to find this converter. Like we find one converter. Like we start with infinite environments, infinite, but in reality our task is to find one object, and that object is this converter, right? And what I'm proposing you here is the converter is just a fake quantum key distribution. Like it's a fake Alice and Bob. No, because that's the idea. The adversary is here. As long as I can make the inputs to this object to be indistinguishable or to fake it as if they come from here, then everything else is going to be the same. Because all of this part, right, which is, let's say, the adversary is here, all of this part is the same in both cases. Because here I have a copy of the adversary. You see? And this part, what it's doing is translating what comes here into what should come here. That's the idea. That's the main underlying idea of the proofs of in composability. Right? So what will happen? Let's define what is the S doing. Right? So let's say, okay, so typically these guys will perform some, share some message, some quantum states, then we'll do some check for correlations, and then we'll do error correction, parameter simplification, or output the keys. So what is this guy doing? This guy doing is basically waiting for receiving keys, for being requested for keys. Right? These guys also will be wait for being requested for keys from the environment. Right? They will not just act by their own. Right? They need to say, okay, I want to run the protocol. Right? So the input from here is just a request of starting the thing, which happens the same in both sides. Right? Once this happens, this will ask this guy for keys, and then as we just saw in the functionality, this will ask the adversary if it's okay to share the keys. Remember, this is what we define the prime. Right? So when this happens here, this is what's going to happen. This guy, when this question is asked to the simulator, the simulator, upon receiving that question, will start running a fake quantum key distribution here. Will create entangled states or photons or whatever, will send into this. This will do whatever it was going to do here, right? And then share to this, and then it will perform some fake correct. Not fake. It's an actual, right? But it's fake in the sense that it's simulated. Right? It is not real, right? That's what I mean. Right? It's not part of a real protocol. And the test will succeed or fail at the same probability, with the same probability that the sex will have succeeded or failed here, because the test is the same. You see? The states that were sent are the same. They follow the same distribution. And depending on the action of the adversary, the success, whether the test succeeds or not, is also the same probability. Right? So if this test does not succeed, then the simulator will say, no, I do not allow. And then the protocol will end. The same way as when this test does not succeed, they will end the protocol here. You see? So it's behaving the same so far. Right? Let's say the test succeeds. Okay, let's say it succeeds. Okay, so then this guy will generate some sort of key, and this guy will end with some information, right? So this will create a state of the form. Let's call let's call A, B, not A, B, let's call KA, because that's how I said KA, KB, and E. right? This will generate this state, which will Ka is what is here, Kb is the state of this, at the end of the protocol, the outcomes, right? And this is the state of this, right? And this is the joint state, which can be entangled, can be whatever. Right? So this is what will end up here, right? What will end up happening here? Well, it's the same, right? Well, no, not exactly the same. They will get with some prime, not call it prime, let's call it real, and let's call it ideal. Right? So, and this status also will be like Ka, Kb, and E. And now, the way we know that this is going to be okay, because these things don't need to necessarily be the same, right? Because, of course, these things, you see, these K0, K1 are connected to the environment. These values are going to be revealed to the environment, whereas these values here are not going anywhere. The values that are going to be revealed to the environment here are what the functionality gave, which has nothing to do with the simulated quantum key distribution. Do you see? Do you get it? So what is going in these wires is related to the execution of this quantum protocol. What is going in these wires is completely random as per the instructions of the functionality. Right? So the analogous version of these wires will be wires that go from here, but these wires are not even, they don't need to even exist, right? So these Ks are lost. So if in any capacity, the state of E depends on the value of Ks, this correlation, then these two guys are going to be distinguishable, because I know that this is going to change depending on what the value here, and I know what the values of here are. But if they are independent, then you cannot say anything. And this is exactly how it is, right? We know that the state rho real, right, is rho ideal too, right? Both rhos are of the form Ka, Kb, E, 1/2 to the n of the square root of K, K, and Ka, K, and Kb. And then some rho E that is uncorrelated with everything else. So this is the indistinguishability base, remember definition, which is proven, right? This was proven by Renner in 2005. So because we know that this is the case, whatever is here cannot depend on the value on the state of these parts here, which means that the only way in which the environment will have been able to distinguish which one of the two sides is interacting is by looking at this and seeing how correlated are this with this. And if they detect difference, then it will be able to tell. But because they are completely independent and uniformly distributed, both of these two things are uniformly distributed. This is uniformly distributed because this is what the quantum key distribution protocol outputs. And these are uniformly distributed because this is what the functionality says. And this thing here, the output of rho E here, it depends only on the action of the environment and the adversary, because the adversary will do whatever, right? So here, whatever it's doing here, it will also do here. And the result of whatever it does is that it will end up with some rho E at the end. But this rho E is independent of the value of the thing. So what it outputs here, the rho E that this guy is able to output here, is the same rho E that this guy is able to output here, because it depends only on the program that the environment and adversary are doing, which is this program and this program. And hence, we can conclude, right, that these two things are indistinguishable for so this obviously these are indistinguishable on K, and this means that this will the ability to distinguish decreases as K increases, and this is the idea. I don't know if this is just meant to be a sketch of a proof, just meant to explain the main idea, right? Obviously not something I will put in a paper, but this is just the idea of how do you achieve the definition that I put, right? Because what I did here, I was not considering many programs or many adversaries. I considered an arbitrary program being run by the environment and the adversary. And what I did is find a converter, a single one program that was able to transform what was happening in the world of the functionality and translate it into what will be happening in the world of the protocol. And if the protocol properties allow, and the functionality is well defined, you may be able to show that, for example, if we're using an expression of this type, you will be able to show that these two things are undistinguished. Like the random variables associated with this, and hence the random variable that this outputs. And because at the end, this is a function of these things here, right? So if you show that the wires in this are indistinguishable from the wires in this, then this is going to be indistinguishable. This is just a function of. And that's the idea. I don't know if you have any question or comment about, I don't know if I am explaining like clearly or not, but this is kind of like the general idea of how a proof gets made in this framework. This fake input has to be convincing. That's the reason that's where the protocol properties enter into play, because not always you not always can do it, right? Most of the time you cannot do it. Not only it's not like you can only, like it's very hard to find protocols for which this can be done. This property, which was, I mean, at the beginning of I actually put it here with the intent of later using it, is that I know that this is the indistinguishability-based definition of security for quantum key distribution, and this is proven to be correct, right? This is proven to happen, and in this expression, you see that the state of the adversary is independent from the state of the value of the keys, like the state of the things. So because it's independent, you cannot use you cannot see one and then see the other and guess if this came from one or the other, because this depends only on the program that the adversary and the environment are running. This depends only on that, and because the simulator has an adversary inside, so it exactly is running the same thing in that part. You see. Just to finish, closing thoughts. Well, simulation security frameworks are very powerful tools for abstracting, not only for abstracting, analyzing the security of cryptographic protocols. Not only they allow us to define security automatically in a way that it is extremely strong, but also it allows us to prove security of bigger protocols automatically if we make proofs of the subroutines, right? So for the universal composition theorem. So it's very good. We want that. Like if every protocol will be universally composable, the world will be but I don't know if it will be a better place, but it will be certainly a easier place for people like me. But with great security comes great requirements. Things not come for free, right? So if you want universally composable security, you have to pay the price somehow. And this usually comes in the form of extra assumptions of very low efficiency in terms of communication, of computation. Sometimes it just cannot be done. Right? It's just straight up, there is no practical ways in which this can be done. But if we accept that, well, universally composable security is desirable, but we should not necessarily keep it as the only kind of security that is acceptable. Right? We should try to be open to evaluate the protocol for their merits and see that UC security is a merit, but cryptography at the end is a game of trade-offs, and it's one of the cool aspects of it. Right? Like you can sacrifice UC security and lower assumptions or lower complexity, whatever, practicality, etc. Some references from the thing, and thank you very much for your attention.